somewhere in the dark between the stars, an ancient object begins a journey long before Earth even exists, older than planets, older than our Sun. It drifts through the Milky Way for billions of years until it finally enters our solar system. Tonight, this quiet traveller reveals a story from a time before our world begins. If this kind of deep space journey is fascinating, please like the video and subscribe to the channel. Across the Milky Way, most small bodies remain unseen. Stars hold attention because they shine, and planets hold attention because they circle close to those stars, but a wider population of colder things drifts between them. Dust moves through giant clouds, ice forms far from stellar heat, pebbles, rocks, and frozen bodies gather in disks around young suns. Some stay where they form, some collide and break, some are thrown away. Over long spans of time, a galaxy does not keep every object tied neatly to the system that made it. Gravity scatters a fraction of that material outward. A body can leave its first sun and continue alone through the larger structure of the galaxy, becoming part of the faint traffic of interstellar space. The Milky Way provides the largest immediate setting for this story. It is a barred spiral galaxy containing hundreds of billions of stars, enormous clouds of gas, dark lanes of dust, and broad stellar populations of different ages. Some stars belong to younger parts of the galactic disk, where heavier chemical elements are more common because earlier generations of stars have enriched the gas. Other stars belong to older populations, moving on different paths and carrying the marks of a more ancient galaxy. Within this mixture, planetary systems form again and again. Around each young star, leftover material settles into a rotating disk. In those disks, grains stick, clumps grow, and small worlds begin. The same process that builds planets also produces countless remnants that never become planets at all. This wider galactic view matters because the object now called 3I/Atlas does not belong to the solar system in the ordinary sense. Observations show that it approaches on a path that is not closed around the Sun. It is not one more comet returning from a long native orbit. It is not a fragment from the Kuiper belt or the Oort cloud. Its speed and trajectory indicate that it comes from outside, passes through, and continues on. In the naming system of the International Astronomical Union, the letter that marks it as interstellar carries that meaning plainly. It is the third confirmed object of this kind ever observed in the solar system, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. That number, only 3, does not mean such visitors are truly rare in the galaxy. It means they are difficult to detect. Interstellar objects are small, dark, and cold. They do not shine by their own light. They appear only when a survey telescope notices a faint moving point against a crowded background of stars. For most of human history, such bodies would have crossed the solar system unseen. Even now, discovery depends on sensitive instruments, repeated sky surveys, quick orbit calculations, and rapid follow-up from many observatories. These observing networks make it possible to notice that the solar system is not sealed off from the rest of the galaxy. Material from elsewhere arrives, and when it does, it carries a physical record of another place and another time. In this broad setting, 3I/Atlas stands out not only because it is interstellar, but because it may also be exceptionally old. Observations indicate that its motion through the galaxy is consistent with a body drawn from an older stellar population, and recent studies place its age in a wide range that can extend beyond the age of the solar system. The solar system forms about 4.5 billion years ago. Some of the oldest known native solids inside it, preserved in meteorites, come from that early beginning. This incoming visitor may preserve material from an even earlier era. It remains uncertain exactly how old the comet is, and no single measurement can state its birthday directly. But the possibility that it formed long before the Sun gives it unusual weight. It is not merely foreign, it may be ancient on a galactic scale. Its direction in the sky adds another layer to the picture. When astronomers first identify it, it is approaching from the general direction of Sagittarius, the part of the sky that lies toward the central region of the Milky Way. That does not mean it comes straight from the galactic center itself. Over immense times, a small body can be deflected by many gravitational influences, and its present incoming line is not a simple arrow back to one birthplace. Still, the geometry places this small comet-like body against the backdrop of a crowded region of the night sky, where stars overlap in crowds and dust veils deeper light. Even its discovery is affected by that setting, because a dim moving object is harder to isolate when the field behind it is so rich. The galactic environment also explains why certainty has limits. A small body wandering for millions or billions of years does not carry an intact label naming its parent star. Orbits evolve, stars move, gravitational encounters shift speeds and directions. By the time such an object reaches the solar system, the original home system may be far away or impossible to identify. What remains available is a different kind of evidence. Its motion can suggest the kind of galactic population from which it may come. Its chemistry can reveal the temperatures and conditions under which it formed. Its activity can show that it is rich in frozen material. Together, these clues allow astronomers to place it within the life of the galaxy, even when one exact origin stays beyond reach. Seen from this outermost scale, the solar system becomes less like an isolated household and more like one address within a vast city of stars. Bodies form in one neighborhood and can appear much later in another. The Sun moves through the galaxy. Other stars do the same. Between them, a thin population of unattached objects crosses the dark. Most remain invisible. Occasionally, one enters the region where human instruments can finally notice it. Then a small moving point of light becomes evidence that the galaxy exchanges material across enormous distances and enormous spans of time. So the oldest object ever to enter the solar system is best understood first not as a local comet, not as a curiosity of one planetary system, but as a galactic traveller. Its present passage is brief, but the setting of that passage is immense. Before it is anything else, it is a body shaped by the long history of the Milky Way itself, carrying forward a fragment of matter that may have begun its journey around another star in a much earlier age of the galaxy. Between stars, space is not truly empty, but it is almost empty by ordinary standards. Matter thins out until even a vast region contains very little substance. A few atoms drift through each cubic centimetre in some areas. In colder and denser clouds, the number rises, but even there the medium remains extraordinarily sparse compared with any environment on a planet or moon. Light from distant stars crosses this medium. Magnetic fields thread through it. High-energy particles move through it. Dust grains float within it. This is the setting through which an interstellar object like 3I/Atlas spends nearly all of its existence. In this deep interstellar passage, cold defines the basic condition. Far from any nearby star, a small body receives little concentrated heat. It still absorbs faint starlight from the galaxy and the afterglow of the early universe. But these sources provide only a weak background. The result is a surface that settles to extremely low temperatures. Frozen materials can remain stable for immense spans of time. Water ice can stay hard. Carbon monoxide and carbon dioxide can remain trapped if buried deeply enough or protected by layers of darker matter. Other frozen compounds also survive in this long cold, preserved because the body spends age after age in a place where energy arrives slowly. That slow arrival of energy matters. A comet or small icy body inside a planetary system often changes when it passes close to its star. Heat reaches the surface, ice turns to gas, dust lifts away, and fresh layers become exposed. In interstellar space, the opposite condition dominates. Change is not absent, but it is gentle, gradual, and spread over extraordinary time. A crust can harden. Fragile materials on the outermost skin can be altered by radiation. Tiny collisions can disturb the surface. Yet the object does not experience the strong cycles of warming and cooling that shape bodies making repeated inner passages around a sun. It lives instead in a long thermal stillness. This stillness helps explain why ancient material can survive. The interior of a small body is a storehouse. Heat does not easily penetrate far inward when the external environment remains so cold. If the body has a dark outer layer made from processed dust, carbon-rich matter, and radiation-altered ice, that layer can act as a shield. Beneath it, more delicate frozen material may stay preserved. Observations of interstellar comets suggest that they can carry ices from very early stages of planetary formation, and 3I/Atlas appears to belong to that same broad class of frozen wanderers. It remains uncertain how thick its altered outer skin may be, but the principle is clear. Long cold travel favours survival. Radiation, however, never disappears from the story. Interstellar space contains cosmic rays, which are fast-moving particles accelerated by energetic astrophysical events, such as supernova explosions. These particles strike exposed surfaces over immense periods. Ultraviolet light from stars also affects the outermost layers. Together, these forms of energy slowly transform matter at the surface. Chemical bonds break and reform. Simple compounds can become more complex residues. Ice near the exterior can be modified into darker, less reflective material. This process does not usually destroy the whole object, but it changes the skin that faces open space. The longer the journey, the more important this quiet processing becomes. Micrometeoroid impacts also play a role. Though the interstellar medium is so thin that collisions are infrequent compared with the dense early stages of a planetary system, still, over spans measured in millions or billions of years, even rare events accumulate. Tiny grains strike the surface at high speed. Each impact can chip, compact, or garden the outermost layer, a term that means slow, overturning and mixing of surface material by repeated small blows. The result is a body that is not frozen in perfect stillness. It ages physically, but it does so with remarkable slowness. The change is steady rather than violent. The motion of such an object through the galaxy is also quiet most of the time. It is not flying through thick clouds or threading narrow hazards one after another. It travels through a broad gravitational landscape shaped by the combined mass of stars, gas, dark matter, and the large-scale structure of the Milky Way. Its path bends gradually as it orbits the galaxy. Nearby stars may pass at great distances and still alter its trajectory slightly. Over enough time, many small gravitational influences can add up. That is why an interstellar body arriving in the solar system cannot easily be traced back in a straight line to a single star. The long drift erases simple maps of origin. For the object itself, This means existence in a state between systems. It no longer belongs to the disk of gas and dust that formed it. It does not orbit a parent star. It does not reside in the settled architecture of planets, moons, rings, and local debris. It is free-floating matter, carrying chemistry from one setting while moving through another. In that sense, interstellar travel is not a voyage with landmarks. It is an extended interval of detachment. Time passes, surface layers darken, and internal ice remains guarded by distance and cold. This is also why age matters differently for such a body than for a planet. A planet is renewed in parts by geology, atmosphere, sunlight, or impacts large enough to reshape a region. A small interstellar comet has no such active system. It preserves by remaining inactive. The less it is heated, the more it can keep from its past. When astronomers suggest that 3I/Atlas may be older than the solar system, they do not mean that its full history sits exposed and easy to read. They mean that the object may have endured through a longer span than native solar system bodies that have been more heavily processed by repeated solar encounters. Its great age and its deep cold work together. So the space between stars is not simply a route. It is a physical environment with its own slow effects. It cools, preserves, darkens, irradiates, and gently alters. It keeps an ancient object intact while also writing a faint record onto its surface. In that near-empty medium, 3I/Atlas spends most of its life as a small, cold body under weak light, carrying old ice through the dark for longer than the existence of the Sun's planetary family, far from the planets, and far from any strong warming by the Sun. There is no hard wall marking the start of the solar system. The transition is real, but it is gradual. A body arriving from interstellar space does not cross a bright line drawn in matter. It enters a region where the Sun begins to matter more and more. Gravity reaches outward without a visible edge, weakening with distance but never fully ending. The solar wind, a flow of charged particles streaming from the Sun, pushes outward and shapes a broad bubble in surrounding space called the heliosphere. Together, these influences create a frontier that is not a border in the ordinary sense, but a zone of changing control. For an object like 3I/Atlas, this frontier is the first local stage of its passage through the solar system. The most important change at this frontier is dynamical rather than visual. In interstellar space, the comet follows a path through the galaxy shaped mainly by the gravitational field of the Milky Way and by the accumulated effects of ancient encounters. As it draws closer to the Sun begins to bend that path. The object is not captured into a closed orbit. Observations show that its trajectory remains hyperbolic, meaning open rather than bound. This word describes a path on which a body swings through a gravitational field and then departs again, carrying enough speed to escape permanently. A native long-period comet may also move on a very stretched path, but it remains tied to the Sun. An interstellar object on a true hyperbolic orbit is different. It comes from outside, turns under solar gravity, and leaves. That distinction becomes visible first in the mathematics of motion before it becomes visible in any dramatic physical change. Astronomers measure the object's position across repeated observations. From those measurements, they determine its speed and direction. Then they compare the orbit with the family of paths expected for native solar system bodies. In the case of 3I/Atlas, the answer is clear. The incoming speed is too great for a body that begins as a resident of the Sun's distant reservoirs. Its motion identifies it as an outsider. The frontier of the solar system therefore becomes not just a location in space, but a test of origin. At this boundary region, orbital geometry reveals that the visitor does not belong to the Sun's long-term population. Even here, however, the Sun has real power. Though it does not trap the comet, it changes the path enough to turn approach into passage. This turning is a simple consequence of gravity acting over great distance. The comet falls inward while already moving rapidly. The Sun draws it faster. Its line curves. If the speed were smaller, capture could become possible under special conditions, especially with help from interactions involving planets. But for an object arriving on the measured track of 3I/Atlas, the inward fall becomes only one half of a transit. The second half, the outward escape, is already built into the orbit from the beginning. The heliosphere adds another element to this frontier. It is a vast bubble carved into the interstellar medium by the solar wind and the Sun's magnetic influence. Its outer shape is not perfectly fixed, because solar activity changes with time and the surrounding interstellar environment also exerts pressure. At great distance, the outward solar wind slows and meets incoming interstellar material. Spacecraft observations from the outer solar system show that this boundary region is complex. For a small body crossing inward, the heliosphere means entry into a domain increasingly shaped by solar particles, solar magnetism, and the diluted but growing influence of sunlight. Yet at the earlier stage of approach, these effects remain weak compared with what the comet will later experience closer to the Sun. The frontier is therefore defined by first contact, not by full transformation. This is why the object remains largely preserved at this stage. The sunlight falling on it is still faint. Surface temperatures remain very low. Frozen materials near or beneath the surface do not yet respond strongly. If activity has begun at all, it is limited and subtle compared with what may come at smaller distances. The frontier region allows astronomers to observe a body that is already inside the Sun's domain but not yet deeply altered by it. That moment is scientifically valuable because it preserves more of the incoming state. The comet carries ancient matter into a zone where it becomes observable before solar heating fully reshapes its visible behavior. There is also a shift in reference. Outside the frontier, the object is best thought of as one small body among the galaxy's free wanderers. Inside it, the same object becomes part of a solar encounter. Its motion is now calculated relative to the Sun. Its future position matters for telescopes on or near Earth. It receives a designation, a catalogue identity, and a place within the temporary record of solar system observation. Human knowledge changes rapidly even though the physical body changes only slowly. A traveller that wanders unrecognized for ages becomes, within days, a named object with an orbit, predicted positions, and a growing archive of images. The frontier is therefore a meeting point between two histories. One history belongs to the comet, which arrives after a journey too long for direct reconstruction in full detail. The other belongs to the solar system, whose instruments, surveys, and observatories are now capable of detecting such arrivals. Neither history cancels the other. The comet remains interstellar. The solar system remains only a brief crossing in its much longer existence. But the crossing is enough to convert an unseen body into an object of study. So this outer solar frontier is not important because it is dramatic to the eye. It is important because it marks the first stage at which the Sun begins to reorganize the motion of a deeply ancient traveller without yet erasing the cold record it carries. 3I/Atlas enters a region of growing solar influence, follows an open path, and remains itself. It is still more a messenger from the galaxy than a comet of the inner Sun. Here, At the threshold of the solar system, the ancient outsider becomes a passing solar visitor. Now the object is no longer only at the frontier of solar influence, it is within the far outer approach, a region of the solar system defined by distance, weakness, and scale. Here the Sun is no longer a distant star among many. It is the central star, but it is still small in the sky and poor in warmth. Its gravity now clearly governs the path of 3I/Atlas, yet its light remains thin. The planets exist much farther inward, and the body moves through a realm where the solar system is present in fact but faint in appearance. This is the first local environment that surrounds the incoming traveller as a solar visitor, rather than simply an interstellar wanderer. The far outer solar system is a place of low energy. Sunlight spreads outward in all directions, and with distance it becomes much weaker. A body here receives only a small fraction of the light that reaches Earth. Illumination still falls on the surface, but it does not dominate the physical state in the way it does near the inner planets. Temperatures remain extremely low. Any warming is modest and gradual. The difference from interstellar space is real, yet not sudden. The object still inhabits a cold regime in which frozen material can remain stable for long periods, especially beneath the outermost surface. The visual character of this region is austere. Darkness fills most of the sky. The Sun is brighter than any other star, but it does not flood the scene. Nearby there are no dense atmospheres, no large moons hanging close overhead, no rings spanning the view. The surrounding space contains dust, scattered small bodies, and traces of plasma carried outward by the solar wind. But everything is spread thinly across enormous distances. The emptiness is not complete, though it often appears so. The solar system in this outer zone is a broad gravitational structure with very little matter per unit of volume. That combination of large influence and low density gives the region its distinctive calm. For 3I/Atlas, this calm means that the most visible changes are still limited. Its orbit bends inward under the Sun's pull, and its speed continues to increase as it falls deeper into the solar system. That change in speed is one of the clearest consequences of entering this region. Gravity performs the work steadily. No engine drives the motion. No collision is needed. The object simply converts gravitational potential into greater velocity as it descends. Yet despite this growing motion, the physical body remains close to its incoming state. Surface layers may begin to respond in small ways, but the far outer approach is still largely a region of preservation. This preservation matters because it gives astronomers a chance to study an interstellar object before stronger solar effects become dominant. At these distances, the body still shows much of what it brings with it from deep space. If it already displays a faint coma, that activity can be compared with models of how volatile materials respond to low levels of solar heating. If it remains quiet, that silence also becomes a clue, suggesting that the most easily released ices are buried, exhausted, or shielded beneath a processed surface layer. In either case, the far outer approach functions as an early observational window. It presents the object in a state that is still mostly ancient and only slightly awakened. The region also places the object within a solar hierarchy that remains mostly invisible but fully real. The major planets lie inward, but their gravity already contributes to the architecture of the system, even when they are far away. Their long-term influence helps define which small bodies remain, which are scattered, and which are lost. In the far outer approach, however, no single planet yet dominates the scene around 3I/Atlas. This Sun is the main organizing force. The object passes through a part of the solar system that is structured more by central control than by close planetary encounter. This gives the path a kind of simplicity. The body is still in the outer reaches, where the main fact is distance from the Sun rather than nearness to any world. Because of that distance, time behaves in a particular way for observers. The object continues moving quickly by human standards, but the region itself is so vast that change in location still unfolds across broad spans of space. A comet can travel millions of kilometers and yet remain within the same general environmental regime. This scale encourages a slow scientific reading. Each set of observations captures only a small part of the inward passage. Repeated measurements are needed to trace the growing brightness, the refinement of the orbit, and the first signs of evolving activity. The far outer approach therefore becomes a period of accumulation in knowledge. Information gathers gradually because the region is large and the processes within it are still relatively subdued. The physical materials of the comet respond accordingly. Dark dust on the surface absorbs what light it can. Ice beneath the crust remains cold. Any gases beginning to escape do so under weak forcing. There is no violent eruption demanded by the environment here. Instead, there is a gentle shift from deep storage toward possible release. The object is still mostly a compact body carrying old ices, mineral grains, and radiation-processed surface material. Its ancient history has not been stripped away. The Sun has announced its presence, but it has not yet fully rewritten the visible character of the visitor. This outer setting also emphasizes how small the object is compared with its surroundings. A nucleus perhaps only a few kilometers across enters a region measured in distances so large that ordinary intuition fails. The Sun controls it from afar. The outer solar system contains it without enclosing it closely. The ratio between body and setting is extreme. That contrast is part of the scientific value of interstellar objects. A small piece of matter, formed elsewhere and possibly earlier than the solar system, can move through an enormous local structure and still preserve distinct evidence of foreign origin. The space around it is vast, but the evidence rides within the body itself. So the far outer approach is a region of first local belonging without true membership. 3I/Atlas is inside the solar system and shaped by the Sun's gravity, yet it remains cold, distant, and only lightly touched by solar energy. The planets are still far inward. The light is still weak. The body moves through a sparse environment where ancient material stays close to the surface of observation. In this broad outer zone, the visitor is held by the solar system only in passage, travelling inward through a realm that is solar in authority but still almost interstellar in feeling. Deeper inward. The path of 3I/Atlas enters the giant planet realm, the broad outer zone where the largest planets of the solar system hold much of the local gravitational structure. Jupiter, Saturn, Uranus, and Neptune do not fill space with matter in any dense sense. They remain separated by immense distances, each surrounded by wide reaches of near emptiness. Yet together they define a powerful region, because their masses shape the motions of smaller bodies across the outer system. Long-period comets, scattered icy remnants, and many unstable objects owe their histories to repeated interactions with these planets. For an interstellar traveller crossing the solar system only once, this realm is therefore not simply a place of passage. It is the zone where planetary gravity becomes a serious part of the local environment. The first fact that matters here is scale. The giant planets are far larger and more massive than the rocky planets of the inner solar system. Jupiter alone contains most of the planetary mass outside the Sun. That mass gives it extraordinary power over the motions of comets and asteroids. Saturn adds a second major gravitational presence, and Uranus and Neptune extend planetary control across the colder outer distances. In this region, the Sun remains the dominant body overall, but the planets can no longer be treated as distant details. Their pull can redirect, accelerate, delay, or eject smaller objects. Over the age of the solar system, they have acted as builders of order and agents of disorder at the same time. For many native comets, this is the realm where long quiet orbits become altered. A body drifting inward from the remote cloud of icy debris beyond the planets may pass near one of the giants and leave on a very different path. It may be sent toward the inner solar system. It may be thrown outward again. In some cases, it may be broken apart by tidal stresses, meaning the differing pull on its near and far sides. In rare circumstances, a close interaction can even help place a body into a shorter orbit around the Sun. The giant planet realm is therefore a sorting ground for icy objects. It takes the slow, distant traffic of the outer solar system and redistributes it into new orbital families. 3 I/Atlas passes through this same region, but it does so under different initial conditions. It is not a native body arriving on a stretched solar orbit. It is an outsider already moving too fast to belong to the Sun. That initial speed changes the meaning of planetary encounters. The giant planets still matter, because any massive body encountered at the right geometry can alter a trajectory. But the available time is short, and capture remains unlikely. To capture an object means to remove enough energy from its motion that it changes from an open path into a bound orbit. A single gravitational interaction can change direction and speed relative to the Sun. But turning an interstellar body into a permanent solar system member is difficult. The object must lose a great deal of orbital energy in exactly the right way. Observations indicate that 3 I/Atlas is not on such a captured path. It remains a passerby. This makes the giant planet realm a test of resilience in motion. The comet crosses a region famous for redirecting smaller bodies, yet it preserves its essential status as interstellar. The path may be bent modestly by planetary gravity depending on the details of distance and geometry, but the larger truth remains unchanged. The solar system does not keep it. The great planets stand as massive presences along the route, but none claims the object as a new satellite or a settled comet of the Sun. It comes in under their influence and continues on. Jupiter gives this region its strongest character. Even from far away, its mass shapes a broad sphere of influence, meaning a surrounding region where its gravity can noticeably affect nearby smaller bodies. Countless comets in the history of astronomy show signs of Jupiter's control. Some are called Jupiter family comets because repeated encounters gradually place them into orbits linked to that planet's influence. For 3 I/Atlas, Jupiter represents the possibility of the strongest planetary disturbance available in the solar system outside the Sun itself. Yet possibility is not the same as outcome. Distance matters, timing matters, a close passage would be important. But the absence of such a passage leaves the object mainly under solar control. In this way, the giant planet realm is governed not only by mass but by spacing. The planets are powerful because they are large, but they are selective because space is vast. That vastness is easy to overlook when thinking about planetary systems. Diagrams often compress the outer solar system into a manageable picture, making the planets seem like close markers along a road. In reality, the spaces between them are enormous. A small comet can move through the giant planet realm without ever approaching a planet closely enough for a dramatic interaction. The region is structured by planetary gravity, but it is not crowded by planetary bodies. This is why 3I/Atlas can traverse the realm without becoming either trapped or torn apart. It is passing through a field of influence rather than a wall of obstacles. The physical appearance of the region remains spare. Sunlight is stronger than in the far outer approach, but still weak compared with the inner system. The giant planets themselves are worlds of gas and ice, wrapped in clouds, rings, and magnetized environments. Yet those local features belong to each planet and do not define the whole corridor between them. The corridor itself remains dark, cold, and thinly populated. Its true substance is gravitational rather than material. Its architecture lies in invisible forces more than visible scenery. For astronomers, this part of the journey helps refine understanding of the object's orbit. Continued observation through the giant planet realm improves the measurement of trajectory, because the body is now well within the solar domain, moving on a track that can be compared precisely against the known positions and masses of the planets. Any tiny deviations matter. They reveal whether outgassing is already adding a slight push, whether planetary perturbations are measurable, and how accurately the future path can be predicted. This is a region where the object becomes dynamically legible. The solar system's largest planets provide the reference framework against which its outsider status becomes even clearer. So the giant planet realm is a place of mass, spacing, and orbital judgment. Here the largest worlds of the solar system display the power that has shaped countless native comets. Yet 3I/Atlas remains distinct from them all. It crosses the outer planetary zone under their influence, but not under their ownership. The giants can alter the route, but they do not end the journey. In their wide and cold dominion, the ancient visitor keeps moving inward, not as a captured member of the solar system, but as a body still defined by passage. As 3I/Atlas continues inward, sunlight changes from a distant background into an active physical force. The shift is gradual, but it is decisive. In the outer regions, the sun governs motion more than surface behavior. Here, deeper into the solar system, the arriving light begins to do work on the body itself. The nucleus remains small, dark, and cold overall. Yet its outer layers no longer sit in near-perfect thermal stillness. Energy now falls on the surface in greater quantity. The change is not a blaze or a sudden awakening. It is a steady increase in absorbed light, and that increase begins to disturb material that has remained frozen through a very long interstellar passage. This process starts at the surface, because light does not penetrate deeply into a dark cometary body. Most of the incoming energy is absorbed or reflected within the uppermost layer. A comet nucleus is usually very dark, darker than many familiar rocks, because its surface contains carbon-rich material, dust, and radiation-processed residues that reflect little sunlight. That darkness matters. A dark surface absorbs more of the light that reaches it, and absorbed light becomes heat. Even so, the warming remains limited to shallow depth at first. The interior stays well insulated from rapid change. This creates a contrast between a surface beginning to respond and a deeper body that still holds the cold of interstellar space. The important physical step in this region is sublimation. Sublimation means that a frozen material changes directly from solid to gas without first becoming liquid. In the near vacuum of space, many cometary ices behave this way when they receive enough heat. Water ice is the best known example, but it is not always the first to respond. More volatile substances, meaning materials that escape more easily at low temperature, can begin to leave the surface or shallow subsurface earlier. Carbon monoxide and carbon dioxide are important examples in many comets. If such ices are present close enough to the surface, even modest warming can start a slow release of gas. for an object like 3I/Atlas. This first solar heating is a delicate phase because the exact response depends on structure as much as on composition. If volatile ice lies openly at the surface, the body can begin outgassing relatively early. Outgassing means the escape of gas from warming material. If the surface is covered by a layer of dust or altered crust, sunlight may warm the exterior while deeper ice remains shielded for longer. Cracks, pores, and weak spots can then become the main path through which gas escapes. The comet is therefore not a simple ball of exposed ice. It is a mixed body of dust, frozen compounds, empty spaces, and hardened outer layers. The first solar heating does not affect every part equally. It acts on an irregular surface and produces an uneven response. That unevenness is one reason comet activity often begins locally. A few patches may warm more efficiently because they face the sun more directly. Darker areas may absorb more heat. Thin crusts may fail in some places while holding in others. Gas then escapes through favoured regions, lifting fine dust and beginning the earliest visible signs of activity. Yet in this stage, the activity still belongs to the surface response itself. The region is defined not by the large cloud that may later surround the nucleus, but by the transition from stored cold to active release. Sunlight begins to translate ancient frozen matter into motion. This transition also reveals something about timescale. An interstellar object may spend millions or billions of years in deep cold, then begin to change measurably over a much shorter interval as it approaches a star. The stored history is long, the solar response is brief. That does not make the response superficial. A small rise in temperature can have large effect when frozen gases stand close to the threshold between remaining trapped and escaping. In this sense, the sun does not need to melt the comet in any ordinary way. It only needs to tip certain materials across that threshold. Once that happens, gas expands outward into the surrounding vacuum, carrying dust with it if the flow is strong enough. The balance between heating and cooling helps control this behavior. Sunlight warms the sunward side, but the nucleus also loses energy by re-radiating heat back into space. Some absorbed energy is used not to raise temperature, but to power sublimation itself. Breaking ice into gas requires energy, and this process can moderate surface warming. The result is a body whose temperature is not determined by distance from the sun alone. Rotation matters, surface texture matters, composition matters. Activity itself matters because escaping gas and lifted dust can change how much light reaches the underlying surface. Even in this early phase, the response is dynamic. Still, the basic picture remains calm. The comet is not yet defined by spectacle. It is defined by conversion. Light becomes heat. Heat reaches shallow frozen layers. Frozen layers release gas. Gas begins to alter the immediate surroundings of the nucleus. That chain is the essence of first solar heating. It is the moment when a body preserved by darkness begins to interact physically with the star it is passing. For scientists, this stage is especially valuable because it links the incoming preserved state to the active cometary state. It allows the body to be studied as both archive and process. The materials escaping from the surface can reveal something about what has remained stored within. At the same time, the pattern of release shows how the surface is built and how deeply ancient ices are buried. The object begins to speak through its activity, but only because sunlight has become strong enough to unlock the first layer of that hidden record. There is no need for violent language to describe this moment. It is one of the quietest important changes in the solar system. A dark object falls inward, light increases, the surface absorbs energy. A frozen compound gives way. gas enters open space, dust loosens. What has travelled unchanged for ages begins, gently and inevitably, to respond to the sun. In this region, 3I/Atlas is no longer only an ancient body arriving from elsewhere. It is becoming an active comet under solar light, one surface patch at a time. Once outgassing becomes steady enough, the space immediately around the nucleus begins to change its character. The body is still small and solid at the centre, but it is no longer alone in a local physical sense. Gas released by solar heating spreads outward from the surface and creates a surrounding envelope called the coma. The word simply means the cloud around an active comet. This cloud is not a static shell. It is a moving, thinning, expanding mixture of gas and dust that forms because frozen material at the nucleus changes state and escapes into open space. In this region of the journey, the coma becomes the main visible environment of 3I/Atlas. The nucleus remains the source, but the cloud becomes the dominant outward expression of what the sun is now drawing from the ancient body. The first thing to understand about the coma is its scale. A comet nucleus may be only a few kilometers across, yet the cloud around it can grow to a size far larger than the solid body itself. This does not happen because the comet suddenly gains mass. It happens because matter that was once packed inside the surface layers is released into vacuum and allowed to spread. Gas molecules move away from the nucleus in all directions, colliding with one another near the source and then becoming more diffuse as the distance increases. Dust grains lifted by the escaping gas join this expanding envelope. The result is an object whose visible presence greatly exceeds the dimensions of its solid heart. Near the nucleus, the coma is densest and most active. Gas is being supplied continuously from the surface, especially from warm or weak regions where sublimation is strongest. In this inner part of the cloud, the flow still carries a strong memory of the surface that produced it. Active patches release more material than quiet ones. Rotation of the nucleus changes which areas face the sun and how long they remain illuminated. Rough terrain, crust thickness, and buried volatile layers all influence the pattern of escape. The coma, therefore, begins not as a perfectly even sphere, but as a physical response to a complicated source. As the gas spreads farther away, these irregular beginnings can blur into a broader envelope. Yet the inner coma still preserves the imprint of local activity on the nucleus. The gas in the coma is made of molecules released from ice that has warmed enough to escape. Water vapor often becomes important in comets that approach the sun more closely, while carbon monoxide, carbon dioxide, and other compounds can contribute at greater distances depending on composition and temperature. Once these molecules enter sunlight, they do not remain unchanged. Solar radiation can split them apart through a process called dissociation, meaning that light breaks a molecule into smaller pieces. Neutral gas can also become ionized, meaning that an atom or molecule loses or gains electrons and becomes electrically charged. Even so, in the coma formation stage, the essential fact is simple. Material once locked in ancient ice now becomes a growing cloud of free molecules around the comet. Dust plays a related but slightly different role. Gas escaping from the surface can drag loose grains upward if the flow is strong enough to overcome the weak gravity of the nucleus and the slight forces holding grains in place. A comet nucleus is small, so its gravity is very weak. This makes it easier for fine particles to be lifted once gas begins to stream outward. Not every grain escapes equally well. Smaller particles can be carried more readily than larger ones, while some heavier material may shift only a little before falling back or remaining near the source. In the early coma, dust thickens the cloud, reflects sunlight, and often contributes strongly to the comet's visibility. The coma is therefore not a cloud of pure gas. It is a combined environment of released vapor and entrained solid grains. Light changes inside this cloud as well. The nucleus itself is dark, but the coma can brighten because its gas and dust scatter sunlight. This does not mean the cloud glows like a lamp by its own power. It becomes visible because sunlight interacts with the released material. Dust reflects and scatters light. Some gas species also emit light at particular wavelengths after absorbing solar energy. Through telescopes and spectrographs, which are instruments that separate light by wavelength, astronomers can study this glow and infer what molecules are present. In this way, the coma acts like an exposed sample of the nucleus. Material that would otherwise remain hidden inside the solid body is carried outward into a form that can be remotely examined. The structure of the coma depends on balance. New gas is always being added from the nucleus as long as solar heating continues. But at the same time, the cloud is always expanding and thinning. Molecules move outward, sunlight changes them, and some are swept farther away by the surrounding space environment. Dust spreads with the gas but follows its own dynamical behavior depending on grain size, shape, and mass. The coma exists because supply and loss operate together. If supply stopped, the cloud would disperse. If solar heating rises, the source can strengthen and the coma can grow denser and broader. So the coma is not a permanent possession of the comet in the way the nucleus is. It is a temporary atmosphere made by ongoing release. This temporary atmosphere is unlike the atmospheres of planets. A planetary atmosphere can be held by gravity over long times and shaped into layers by pressure, temperature, and circulation. The coma is much looser and less confined. It is not resting stably around the nucleus. It is streaming outward into space. Its density drops rapidly with distance. Its edges are not sharp. Its form is continuously renewed rather than continuously contained. Yet for an active comet, it becomes the immediate environment through which all later released material must pass. It is the local medium of the cometary state. For 3I/Atlas, coma formation is especially important because it transforms the object from a small ancient body responding at the surface into a much larger observable system. The nucleus still contains the record of deep time, but the coma makes that record accessible. Molecules from old ice, dust from preserved surface layers, and the timing of release under sunlight all enter view through this cloud. The comet becomes readable because it surrounds itself with matter drawn from within. So in this region, the key change is not the loss of the nucleus into spectacle, but the growth of an envelope that reveals the nucleus more clearly than bare darkness could. A solid body only a few kilometers across begins to wear a cloud vastly larger than itself. Gas spreads, dust joins it, sunlight passes through it, and the surrounding space near the comet is no longer empty. Around the ancient visitor, the coma forms as the first full outward atmosphere of passage, a visible and expanding record of material that has waited in cold storage for ages and now enters the light. Beyond the coma, the released material is no longer only a surrounding cloud. It begins to stretch outward into more extended forms, and these forms give the comet one of its most recognizable features. What had been a local envelope around the nucleus now becomes a flow shaped by forces acting differently on different kinds of matter. Dust grains and gas do not behave in the same way once they leave the inner coma. They separate into distinct patterns because sunlight, solar radiation pressure, and the solar wind do not push on them equally. In this region, 3I/Atlas becomes not just a nucleus inside a cloud, but a body drawing matter outward into tails. The basic reason for tail formation is simple. Material released from the nucleus enters open space while the comet itself continues moving along its orbit around the Sun. Once outside the immediate grip of the nucleus, each particle and molecule begins responding to the larger solar environment. The Sun supplies not only heat but also outward pressure in the form of light and a constant stream of charged particles known as the solar wind. These influences do not act with the same strength on all released material. A tiny dust grain with mass and surface area behaves one way. An ion, meaning an electrically charged atom or molecule, behaves another way. Because of this difference, the outward flow of material separates into distinct structures rather than remaining one blended stream. The dust tail is usually the broader and softer looking of the two main tails. It forms from solid particles that are dragged away from the nucleus when escaping gas lifts them from the surface. Once free, those grains still carry inertia, which means they tend to continue moving in a path related to the comet's own motion. At the same time, sunlight exerts a gentle outward force on them. This is called radiation pressure. It is not strong enough to stop behaving like gravity's weaker counterpart in any dramatic sense. But over time it matters. It pushes the grains away from the Sun while their original orbital motion carries them forward. The result is a tail that often appears wide and curved rather than straight. That curvature reveals the balance of forces. Larger grains have more mass relative to the push they receive from sunlight, so they respond more slowly and tend to remain closer to the comet's orbital path. Smaller grains are pushed more efficiently and can spread farther outward. Because many grain sizes are released together, the dust tail becomes a layered stream of particles following slightly different trajectories. It is not a rigid beam. It is a dispersed trail of solid matter, broadening with distance and often bending gently in the direction shaped by both solar radiation and the comet's motion. In images, this tail can look white or yellowish, because it shines by reflected sunlight. The ion tail forms differently. Gas released from the coma begins as neutral molecules, but sunlight can break and ionize this material. Once molecules become charged, they no longer respond mainly as drifting neutral gas. They become strongly affected by the solar wind and by the magnetic field carried within that wind. The solar wind streams outward from the Sun at high speed, and charged particles from the comet are swept into that outward flow. Because of this, the ion tail tends to point much more directly away from the Sun. It is often narrower and straighter than the dust tail. Its form reflects the motion of plasma, meaning electrically charged gas, rather than the slower drift of solid grains. This distinction between the two tails explains a common misunderstanding. A comet's tail does not simply stream behind it the way smoke trails behind a moving object in air. In space, there is no dense atmosphere around the comet to create that kind of wake. Instead, the tails are organized mainly by solar forces. If the comet is moving away from the Sun, the tails can even appear in front of the direction of travel while still pointing away from the Sun. The geometry comes from the orientation of radiation pressure and solar wind, not from ordinary resistance by surrounding matter. The comet moves on its path, but its tails are continually being drawn outward from the Sun. The dust tail and ion tail also differ in texture. Dust produces a fuller, hazier appearance because it is made of many solid grains scattering sunlight across a wider region. The ion tail can look thinner, cleaner, and more structured. This is partly because plasma responds strongly to magnetic conditions in the solar wind. Changes in that flow can create ripples, rays, and even disconnection events in some comets, where part of the ion tail appears to break and drift away after magnetic disturbances. Even when such events are not observed directly, The ion tail remains the more delicate and fast-changing of the two major tails. It belongs to a solar wind environment that is itself variable and dynamic. The outward drawing of matter therefore becomes a sorting process. Released material does not simply leave the coma and remain mixed. It is separated by size, mass, charge, and response to the sun. Dust grains spread into a curved reflective tail. Ionized gas is carried into a straighter plasma tail. Both originate from the same ancient nucleus, but each tail displays a different physical rule. One tells the story of sunlight acting on tiny solids. The other tells the story of solar wind acting on charged gas. Together they show that the comet is not only active, but physically readable in two parallel ways. For 3I/Atlas, this is especially important because the tails are extensions of interior history. Dust grains may preserve texture, mineral content, and the record of surface processing. Gaze in the ion tail reveals which volatile substances are being released and altered by sunlight. The tails are therefore not decorative appendages. They are moving samples of material drawn from the body and spread into space where telescopes can study them. Spectra of gases, measurements of brightness, and the shape of the tails all help astronomers infer what kind of material the comet contains and how that material responds to solar conditions. Yet even here the comet remains fundamentally small at the center. The tails can grow to immense apparent lengths compared with the nucleus, but they are created by constant replenishment. Material is always moving outward, thinning as it goes, while new material replaces it near the head of the comet. The tails are processes rather than possessions. They exist because the sun continues to pull ancient matter out into visible form. So in this region, matter released from 3I/Atlas becomes directional. Dust bends into a broad curved stream under sunlight. Ionized gas is swept into a straighter tail under the solar wind. What begins as a shared cloud around the nucleus separates into distinct outward paths. The comet's ancient material enters the space around it and is sorted by the physics of light, charge, and motion, forming long extensions that point away from the sun and make the invisible forces of the solar system briefly visible. At the center of everything now visible around 3I/Atlas lies the nucleus, the small solid body from which the coma and tails arise. After the cloud, the dust, and the outward drawn streams of material, the inward path reaches the compact source itself. The nucleus is the comet in its most concentrated form. It is not the broad glow seen through a telescope. It is not the long visible extension pointing away from the sun. It is the solid heart. The piece of matter that has travelled through interstellar space for an immense span of time and now passes through the solar system while slowly shedding material from its exterior. This nucleus is small by planetary standards. Even the upper estimates place it at only a few kilometers across, and current observations leave its exact size uncertain. The best constraints show that it is far smaller than a moon, far smaller than any planet, and small enough that its own gravity is weak. That weakness matters because it shapes nearly every physical property of the body as a form. A planet can force itself into a sphere when its mass becomes great enough for gravity to overcome the strength of rock or ice. A comet nucleus cannot do that. It remains irregular because the material strength of its substance dominates over its own self-gravity. The result is a body whose shape is set not by smooth gravitational rounding but by formation, collision history, loss of material, and structural weakness. This is why comet nuclei are generally expected to be lumpy, uneven, and asymmetrical rather than neatly spherical. The nucleus of 3I/Atlas is not yet resolved in direct visual detail the way a spacecraft might reveal a nearby comet. so its exact outline remains uncertain. Telescopes at great distance do not simply present a clear picture of the bare solid body. The surrounding coma complicates the measurement because light from dust and gas blends with light from the nucleus itself. Astronomers therefore infer size and form indirectly, using brightness, high-resolution imaging, and models that attempt to separate the compact central contribution from the broader surrounding glow. This means that the nucleus can be constrained, but not yet seen in full detail. It is known as a real solid body, but still imperfectly measured as an exact shape. That uncertainty is scientifically ordinary for a distant comet. The object is small, the environment around it is active, and the observing geometry changes as it moves. What matters most at this stage is not a perfect contour, but the basic physical fact of compactness. A nucleus is the concentrated reservoir from which everything else follows. It holds the mass. It provides the surface from which gas escapes. It gives the comet a center of gravity. Weak though that gravity may be, it preserves the body's identity as one object rather than a diffuse cloud. Without the nucleus, there is no comet in the strict sense, only expanding debris. Its darkness is another defining feature. Comet nuclei are among the least reflective bodies in the solar system. They often reflect only a small fraction of the sunlight that reaches them. This makes them difficult to observe and helps explain why they can remain hidden until activity increases their visibility. A dark nucleus absorbs much of the light falling on it, rather than sending that light back outward. The darkness does not mean the body is made of one single dark substance. It means the surface as a whole presents a low reflectivity, probably because of mixtures of dust, carbon-rich residues, and processed material that have accumulated over long exposure to radiation and past heating. In form, this makes the nucleus less like a bright icy object and more like a blackened remnant carrying frost within rather than displaying it openly. The weakness of the nucleus's gravity also determines how material behaves near it. A person standing on such a body, if such a thing were possible, would not experience anything like the pull of a planet. Escape speeds would be very low. A particle lifted from the surface by even a modest gas flow might leave permanently. This is part of the reason a comet can build such a broad coma from such a small solid core. The nucleus is large enough to hold itself together, yet too small to hold released gas and dust in any substantial atmospheric envelope. Matter that departs does not settle into stable confinement. It escapes into the surrounding space and becomes the visible structure already described in earlier regions. In this sense, the nucleus is both firm and fragile. It is firm because it survives long travel through interstellar space as a coherent object. It is fragile because it is lightly bound, irregular, and vulnerable to loss of material once sunlight begins to act on it. Its existence over immense time shows structural endurance, but that endurance is not the same as strength in the way a large rocky planet is strong. A comet nucleus is more like a preserved aggregation, a compact but delicate body whose continued coherence depends on low gravity, low temperature, and the absence of severe disturbance. Rotation likely adds another layer to its form, even if the exact rotation state is not yet fully settled. Most comet nuclei spin, and that spin changes which parts of the surface face the sun over time. The effect is to give the body alternating periods of illumination and shadow. On an irregular nucleus, rotation can also complicate the apparent brightness seen from Earth because different cross-sections turn toward the observer at different moments. This is one of the clues astronomers use when trying to infer shape. A more elongated body can brighten and dim more noticeably as it rotates, while a more compact form may vary less. Yet for 3I/Atlas, the surrounding activity and the limits of observation mean that such deductions remain provisional. The nucleus is understood as rotating matter, but not yet as a fully mapped object. So the nucleus is defined less by perfect measurement than by physical role. It is the solid center, the small dark body, the irregular source from which all visible activity emerges. It is measured in kilometers, not in hundreds or thousands of kilometers. It does not command space by size, only by origin. Around it the coma expands, and beyond it the tails stretch far outward. But those structures remain temporary extensions. The nucleus alone is the ancient traveller itself, compact enough to endure, dark enough to hide, and small enough that even powerful telescopes must still work indirectly to understand its true dimensions and shape. Beneath the dark surface of 3I/Atlas, the nucleus can be understood as a storehouse of ancient ice mixed with dust and rocky material. This does not mean a single clean block of one frozen substance. A comet nucleus is a composite body. Different frozen compounds occupy pores, grains, layers, and pockets inside a small irregular mass that forms in extreme cold. In this region of the inward path, the focus rests on that frozen inventory itself, the mixture of materials that survives long interstellar travel and now escapes in small amounts under solar heating, revealing something about the conditions in which the body first forms. The most familiar cometary ice is water ice, and it is almost certainly part of the nucleus of 3I/Atlas as well. Water is common in the cold chemistry of young planetary systems, and in many comets it becomes the dominant gas closer to the Sun. But water is not the whole story. Other frozen molecules can be present beside it, and these other materials are especially important in a body that begins to show activity while still far from strong solar warmth. Carbon dioxide and carbon monoxide are two important examples. They are more volatile, meaning they escape more easily at lower temperatures. Observations of 3I/Atlas indicate that its coma is unusually rich in carbon dioxide relative to water and carbon monoxide. And that pattern suggests a nucleus with a substantial inventory of carbon-bearing ice. This does not mean that the bulk interior can be read in a perfectly direct way from the gas now leaving the comet. What telescopes measure is the material reaching the coma, and that material depends on depth, heating, surface structure, and the pathways through which gas escapes. Even so, the released gases are still clues to the frozen mixture below. They show that the nucleus is not chemically simple. It contains a combination of water ice, carbon dioxide ice, carbon monoxide ice, and smaller amounts of other frozen compounds. One sulfur-bearing molecule, carbonyl sulfide, has also been identified in the gas around the comet. Water ice grains are seen as well. Together, these observations support the picture of a nucleus made not of one dominant frozen ingredient alone, but of several volatile reservoirs preserved side by side. Such a mixture points toward a very cold birthplace. In a young planetary disk around a star, different compounds condense or freeze at different temperatures and distances from the central heat source. Close to the star, only the least easily vaporized solids can remain stable. Farther out, water ice becomes stable. Farther still, at lower temperatures, carbon dioxide and carbon monoxide can freeze efficiently. A nucleus unusually rich in carbon dioxide and still carrying carbon monoxide and water together suggests formation in a cold outer region where these compounds can be incorporated into growing solids. The exact distance from its parent star remains unknown, but the chemistry indicates an environment well removed from strong warmth. The way these ices are stored inside the nucleus is also important. They're not expected to sit as large clear layers like ice in a terrestrial cliff. In a comet, frozen compounds are usually mixed with fine mineral grains, darker carbon-rich material, and empty space between particles. Some ice may coat grains, some may fill pores, some may be trapped under crusts formed later by surface processing. As the nucleus warms, the most accessible volatile material escapes first, while deeper or less exposed ice can remain hidden. This means that the nucleus is chemically mixed but physically uneven. That uneven storage helps explain why carbon dioxide can appear especially prominent in 3I/Atlas. Carbon dioxide may simply be abundant in the nucleus, but it may also be better placed to escape at the temperatures reached during observation. Water ice often needs stronger heating before it outgasses strongly. If the surface crust limits the flow of heat downward, then water can remain partly locked below while carbon dioxide and carbon monoxide, which are easier to release, dominate the activity. Observations therefore indicate a carbon dioxide-rich active layer. While it remains uncertain how closely that active layer matches the full untouched interior, the nucleus preserves a chemical record, but the record is exposed selectively. Long interstellar travel may also alter the outer portion of that record. Cosmic rays and ultraviolet radiation can slowly process exposed ice and dust over immense spans of time. Such processing can change the balance between carbon-bearing species near the surface and help produce darker residues. This possibility matters for 3I/Atlas because the comet may have spent an extremely long time between stars. If so, the upper layers of the nucleus may no longer represent pristine material in a simple way. Yet even a processed outer layer still tells a story. It records the interaction between original ice mixture and deep time in interstellar space. What remains most striking is the survival of so much volatile material at all. To be volatile is to be easy to lose under heat, and yet these compounds survive because the comet spends nearly all of its existence in deep cold. The nucleus acts as a freezer sustained by distance. The result is a body that can carry an old low-temperature inventory across the galaxy and reveal it only when sunlight reaches the surface during a brief solar passage. The ancient ice mixture therefore has two meanings at once. It is a real combination of frozen water, carbon dioxide, carbon monoxide, and other minor compounds bound into the body. It is also a record of environment. It speaks of low temperatures, weak early heating, and chemical sorting in the outer zones of a young planetary disk. Even with uncertainty about the untouched deep interior, the observed gases show that 3I/Atlas contains a substantial store of primitive frozen material. Its nucleus is not merely old rock carrying a little frost. It is an ice-rich archive, assembled in severe cold and preserved across immense time. In this region, then, the comet is best understood as a frozen mixture before it is understood as anything else. The activity around it matters because it reveals that mixture, but the mixture itself is the deeper fact. Within the dark, irregular nucleus lies a reservoir of ancient volatile matter, locked together in uneven layers and pores, carrying the chemical memory of a cold birthplace around another star. That memory survives not as a single pure ice, but as a blended inventory of frozen substances that remain present after ages in the dark and now emerge, piece by piece, into sunlight. When ancient ice leaves the nucleus of 3I/Atlas, it does not emerge alone. Mixed with the escaping gas are solid particles, and these particles matter because they preserve the physical texture of the body in a way gas cannot. Gas reveals which volatile substances are being released, but dust reveals how the nucleus is built as a material object. In this region of the inward path, The focus narrows from the whole frozen mixture to the grains themselves. The small solids lifted from the surface and shallow subsurface, carried outward into the coma and spread into the dust tail. These grains are fragments of structure. They are pieces of the comet's skin and near-surface interior, and they carry a physical memory of formation, storage, and breakdown. Cometary dust is not one uniform substance. It includes mineral grains, darker carbon-rich material, and aggregates, meaning clumps made from many smaller particles stuck together. Some grains may be compact and relatively dense. Others may be porous, fragile, and loosely assembled. This variation matters because it affects how easily grains are sifted, how they scatter sunlight, and how they survive once released. The dust around 3I/Atlas is therefore not best understood as simple powder. It is a population of solid particles with different sizes, shapes, textures, and strengths, all derived from the nucleus and all responding in different ways to the same solar forcing. The pathway by which this dust enters space begins at the surface. As sunlight warms volatile rich layers beneath or within the outer crust, gas escapes through pores, cracks, and weak zones. If the upward flow is strong enough, it drags small grains with it. Because the gravity of the nucleus is weak, the threshold for lifting fine material is low compared with larger planetary bodies. A particle does not need a powerful push to escape permanently, yet the process is still selective. The smallest grains are easiest to lift. Larger grains require stronger gas flow. Some material may be loosened and shifted without truly escaping, while the finest dust is carried away and joins the coma. This sorting by size is one of the first clues to the physical nature of the surface. What that surface yields tells a story about its texture. A surface made mainly of solid exposed ice would not behave like one covered by a darker crust of dust-rich residue. A compact crust resists disruption. A loose mantle, meaning a blanket of unconsolidated grains, can be disturbed more readily. If gas is trapped below a denser layer, pressure can build and then vent through openings, releasing bursts of dust from certain patches. If the surface is more porous, gas may seep through many tiny paths and lift material more gently. The observed dust therefore acts as evidence for how tightly or loosely the surface is assembled. It does not provide a perfect map, but it does reveal whether the nucleus behaves more like a hard shell, a crumbly aggregate, or a mixture of both. Porosity is especially important here. A porous material contains many small empty spaces within it. In a comet nucleus, porosity allows gas to move through the body and also weakens the material mechanically. A highly porous structure is light for its size and often fragile. Many comet nuclei are thought to be porous because they form from gentle accumulation in cold outer disks rather than by intense compression. The dust released from 3I/Atlas likely reflects this kind of origin. If many grains are themselves aggregates rather than single compact crystals, that suggests the nucleus contains preserved clumps assembled under low-energy conditions long ago. The comet then becomes not just old matter, but softly assembled old matter. The fragility of the dust also matters once the grains are free. Some particles remain intact, while others break apart under heating. Collisions, or stress from being accelerated by escaping gas. This means the dust environment around the comet can evolve even after release. A larger fragile aggregate may disintegrate into smaller grains, changing how the coma and dust tail scatter light. A more compact grain may travel farther unchanged. In this way, the dust record includes both inherited structure and ongoing modification. It preserves the past, but not passively. It continues to respond to solar passage. Brightness observations help astronomers infer something about these particles without touching them directly. Dust scatters sunlight, and the amount and pattern of that scattering depend on grain size, shape, and composition. Fine grains often brighten the coma efficiently because they offer a large total surface area. Larger grains contribute differently, sometimes producing broader structures or lingering closer to the comet's path. By studying the brightness profile of the coma and tail, astronomers estimate how much dust is being produced and what general size distribution may be present. Such work does not identify every grain, but it turns light into evidence about texture. A cloud of dust is also a cloud of structural information. This structural information reaches backward into the comet's history. In the early disk around another star, grains collide and stick. Some remain small, some grow into aggregates, some become mixed with ices condensing in severe cold. If 3I/Atlas preserves material from that environment, then the dust it releases may still carry the imprint of those early assembly conditions. A fragile aggregate can be a fossil of gentle sticking in a cold disk. A more altered compact particle may record later processing or repeated surface exposure. Even after an immense interstellar journey, the dust still offers a tactile kind of evidence, not of touch in any human sense, but of physical arrangement. Surface processing over long time also leaves marks on the grain record. Radiation in interstellar space can darken exposed material and alter the outer layers of grains. Repeated heating during the present solar passage can dry, crack, or separate near-surface aggregates. As a result, the dust released now is not necessarily pristine in every detail. Some grains may be ancient and little changed. Others may be fragments of a crust produced by long exposure. This does not weaken their value, it adds depth to it. The dust reveals both original assembly and later aging. So these small particles are more than debris. They are solid evidence of how the nucleus is put together. They show that the comet is not a smooth frozen stone, but a structured mixture of fine matter, clumps, pores, and weakly bound layers. They reveal that the body likely forms under low-energy cold conditions and survives by remaining mostly undisturbed. When sunlight finally loosens grains from the surface, the released dust becomes a readable sample of the nucleus's texture. In this region, then, 3I/Atlas is understood through the grains it sheds. Each lifted particle is a fragment of physical history. Together the dust records surface strength, porosity, aggregation, and breakdown. Gas tells what the comet contains in volatile form, but dust tells how that content is physically packed. Through these tiny solids, the ancient traveller reveals not only what it is made of, but how its matter has been assembled, preserved, and slowly taken apart. Inside the gas released from 3I/Atlas, some of the most revealing clues are not whole molecules alone, but isotopes. An isotope is a version of the same element with a different mass because its nucleus contains a different number of neutrons. Chemically, isotopes behave in very similar ways. Physically, however, they do not distribute themselves identically in every environment. Under certain temperatures and conditions, one isotope can be favored over another by small but measurable amounts. Those small differences matter because they preserve a memory of formation. In this region of the inward path, the focus narrows to those isotopic clues and to what they can say about the cold birthplace of this ancient comet. One of the most important measurements involves hydrogen in water. Ordinary hydrogen contains only a proton in its nucleus. Deuterium is a heavier form of hydrogen that also contains a neutron. Water made with deuterium in place of ordinary hydrogen is sometimes called heavy water, though in a comet it is present only in small fractions. Even so, the ratio between deuterium-bearing water and ordinary water is extremely valuable. Observations of 3I/Atlas indicate that its water is unusually rich in deuterium compared with known solar system comets. That enrichment does not arise at random. It points toward very cold formation conditions, because low temperatures can favor chemical pathways that place deuterium into molecules more readily than warmer conditions do. This matters because temperature leaves a chemical imprint long after the original environment has vanished. In a cold outer disk around a young star, ion-molecule reactions can proceed in ways that enrich deuterium in icy compounds. If later heating is limited, that enrichment can remain preserved. A comet carrying such water into another planetary system therefore carries evidence of cold chemistry in its own molecules. For 3I/Atlas, the deuterium signal suggests that a substantial fraction of its water forms or is processed in an environment of deep cold, likely colder than the conditions recorded by most familiar solar system comets. The exact temperature cannot be stated as one perfect value from a single ratio alone, but the direction of the evidence is clear. The ice record points towards severe cold. Carbon isotopes offer another important clue. Carbon occurs mainly as carbon-12 and carbon-13. Both forms participate in the chemistry of carbon monoxide and carbon dioxide, which are major volatile species in 3I/Atlas. Measurements indicate that the ratios involving these carbon isotopes in the comet differ from what is usually seen in solar system comets and in nearby interstellar material. Such an anomaly matters because carbon isotope ratios can reflect both the larger chemical history of the gas from which a body forms and the local fractionation processes that operate in cold environments. Fractionation means that physical or chemical processes sort isotopes unevenly, leaving one form relatively more common in a given material than another. In 3I/Atlas, the unusual carbon isotope pattern suggests that the comet does not simply sample the same reservoir from which the solar system forms. Its material appears to preserve a distinct isotopic environment. This does not identify a specific parent star. It does not provide a map back to one exact birthplace. What it does provide is a chemical difference large enough to show that the object forms in a setting not closely matched by the comet reservoirs known around the Sun. Carbon in this nucleus, as seen through the escaping gases, carries a signature of other conditions, likely earlier and colder, and perhaps linked to a part of the galaxy with a different chemical history. Nitrogen adds a further layer. Nitrogen isotopes can be studied through molecules such as cyanogen in the coma. Observations of 3I/Atlas indicate unusually high nitrogen isotope ratios compared with typical solar system values. Nitrogen is especially useful because its isotopic balance can be sensitive to the environment in which nitrogen-bearing molecules form and are later preserved. A high enrichment in the heavier form again points away from ordinary solar system comet chemistry and toward a chemically distinct origin. When hydrogen, carbon, and nitrogen all suggest something unusual at the same time, the case becomes stronger. No single ratio has to bear the full interpretive weight on its own. Taken together, these isotope measurements suggest three broad conclusions. First, the ice chemistry of 3I/Atlas forms under very cold conditions. Second, the source material likely belongs to an environment chemically different from the one that produces most known solar system comets. Third, the body preserves that record with remarkable fidelity despite its long exposure to interstellar space. This does not mean the isotopic story is perfectly untouched. Surface processing, selective sublimation, and the fact that measurements are made in the coma rather than directly inside the untouched nucleus all introduce caution. The escaping gas represents accessible material, not necessarily the exact average of the deepest interior. Even so, the observed ratios are too distinctive to ignore. There is also a wider galactic implication. Isotopic patterns can reflect not only local temperature in a disk, but also the composition of the larger interstellar material from which that disk forms. A region with lower metal abundance, meaning a lower proportion of elements heavier than hydrogen and helium, can leave different chemical balances in the solids and gases that later assemble into comets. The isotope data from 3I/Atlas are consistent with such a metal-poor environment. That does not prove one detailed history, but it supports the picture of formation in an older part of the galaxy, where chemical enrichment has not yet reached the levels familiar in the Sun's neighbourhood. This is why isotopes are so powerful. They are quiet evidence. They do not announce themselves in the shape of the nucleus or in the length of the tail. They sit inside molecules and must be measured with careful spectroscopy. Yet once measured, they reveal conditions that the eye could never see. They allow a small active comet to be read as a frozen chemical document in 3I/Atlas. That document indicates ice made in deep cold, carbon chemistry unlike known solar system bodies, and nitrogen signatures that strengthen the case for a distinct and ancient origin. So in this region, the comet becomes legible at one of the finest levels available from afar. Its isotopes show that not all hydrogen is the same, not all carbon is the same, and not all nitrogen is the same in the history written into its ices. Through those subtle differences in mass, 3I/Atlas reveals that it forms in a cold and chemically uncommon environment, carrying within its released gases a precise but partial memory of where and how its matter first takes shape. The age of 3I/Atlas cannot be read directly from the surface, the way a date might be written on a stone. No layer announces a year of formation. No instrument measures an exact birthday from afar. Instead, one of the most important clues comes from motion. The comet moves through the solar system on a path that can be measured precisely, and that measured path can be extended into the wider context of the Milky Way. In this region of the inward path, the focus turns from material composition to dynamics, meaning motion under gravity. The question is not how old one molecule is, but what the comet's speed and galactic behaviour imply about the age of the environment from which it likely comes. The first part of that reasoning begins with the object's interstellar speed. 3I/Atlas does not drift into the solar system slowly. Before the Sun bends its path and increases its speed further, it already approaches with a substantial velocity relative to the Sun. That fact alone shows that it is not a native comet returning from a distant solar reservoir. But velocity contains more information than origin alone. In the Milky Way, stars and the small bodies associated with them do not all move in the same way forever. Over very long spans of time, repeated gravitational encounters gradually stir stellar populations. Older populations tend to show greater random motion relative to the local standard of rest, which is the average motion of stars in the Sun's galactic neighbourhood. This broad statistical relation is called an age-velocity relation. The idea is simple even if the details are technical. A younger star population begins with a certain organised motion in the galactic disk. As time passes, gravitational interactions with giant molecular clouds, spiral structure, and other mass concentrations slowly scatter those motions. The population becomes dynamically hotter, meaning not hotter in temperature, but more spread out in speed and direction. Older stars therefore tend, on average, to move with larger velocity dispersions than younger stars. If an interstellar object shares the motion pattern of one of these older populations, then it may also originate from a correspondingly older system. This is where 3I/Atlas becomes unusual. Its incoming galactic motion appears more consistent with the Milky Way's thick disk than with the younger thin disk where the Sun resides. The thick disk is an older stellar population. Its stars typically move with larger vertical and random velocities and often have lower abundances of heavy elements than thin disk stars, if the comet's motion is read in that context. Then it likely comes from a system born in an earlier epoch of the galaxy. That does not yield one exact age, but it shifts the probability strongly away from a young origin. Instead of being merely older than a typical active comet, it may be far older than the solar system itself. This conclusion remains statistical, and that caution is essential. Motion does not function like a clock built into the comet. The object is not dated because one simple formula turns speed into years. Rather, astronomers compare its measured galactic velocity with modelled populations of stars and interstellar objects. If an object falls within the range expected for bodies associated with older populations, then an older age becomes more likely. In recent work on 3I/Atlas, this kind of analysis suggests an age measured not in a few billion years alone, but in a range that can extend well beyond the Sun's age of about 4.5 billion years. Some estimates place the likely age above 7 billion years, while broader ranges reach still higher. The exact number remains uncertain, but the trend is robust. Its motion points old. The reason this is so significant is that motion is one of the few things preserved even when direct origin is lost. A small body wandering for immense time may no longer be traceable to a specific star. Parent systems move, stars drift through the galaxy. Gravitational encounters slowly alter trajectories. After enough time, the path becomes mixed into the wider galactic flow. Yet this same mixing is part of what age from motion reads. A body that has spent long spans within older, dynamical populations carries the kinematic character of those populations. It may no longer remember its exact home address, but it still moves like matter from an old neighbourhood. There is also a link between motion and chemistry. The thick disk does not differ from the thin disk only in speed. It also differs in typical chemical history. Older stellar populations form when the galaxy contains fewer heavy elements than it does later. If 3I/Atlas both moves like an object from an older population and shows isotopic and volatile signatures, unlike familiar solar system comets, then the two lines of evidence strengthen one another. Dynamics alone suggests age. Chemistry alone suggests a distinct and ancient environment. Together they make the case more persuasive, though still not absolute. Even so, careful limits remain. The comet's present motion has not remained untouched since formation. It may have experienced gravitational encounters after ejection from its birth system. Passing stars and large clouds can perturb a small body over vast times. These influences can modify its trajectory and make backward reconstruction difficult. That is why age from motion is expressed in probabilities rather than certainties. The motion indicates likely membership in an old galactic population, but it does not prove that every kilometre per second of present velocity comes straight from the original parent system. It reveals the broad historical setting, not a perfect personal history. This is still enough to make 3I/Atlas remarkable. Most objects observed inside the solar system are tied to the Sun, and therefore to one shared formation era. Even when native materials preserve ancient chemistry, they usually belong to the same broad age as the solar system itself. an interstellar body whose motion suggests origin in a much older part of the galaxy, breaks that pattern. It introduces a new timescale into solar observation. The comet is seen now, during one brief passage, but the dynamical evidence implies that its story begins in a period of galactic history long before the Sun forms. So, age from motion is not a dramatic revelation. It is a quiet inference built from orbital precision, galactic dynamics, and comparison with stellar populations. The comet enters the solar system at high speed. That speed is measured. Its motion is set within the larger structure of the Milky Way. That structure contains populations of different ages. The match points toward an old origin, likely in the thick disk, and possibly toward a body older than any previously observed visitor of this kind. The exact age remains uncertain, but the inward-moving evidence is clear enough to change how the object is understood. 3. I/Atlas is not only foreign in space. By its motion, it appears foreign in time. The path now turns inward beyond the comet itself, and toward the system that most likely makes it long ago. That system is lost in any direct sense. No telescope can point to one star and identify it with confidence as the birthplace of 3I/Atlas. Too much time has passed. Stars move through the Milky Way. Their planetary systems move with them, and small bodies ejected from those systems continue on altered paths of their own. Yet the parent environment can still be described in broad physical terms. It is most likely another young planetary system, centered on another star, surrounded in its early age by a disk of gas, dust, rock, and ice. In this region of the inward path, the comet is understood not as a visitor in the solar system, but as leftover material from a vanished local history around another sun. Every planetary system begins with a cloud collapsing under gravity. As the cloud contracts, most of the mass gathers into the forming star, while the remaining material flattens into a rotating disk around it. This disk is the birth setting for planets, moons, comets, and countless smaller remnants. Dust grains collide and stick. Ices condense in cold regions. Pebbles grow into larger clumps. Some clumps become planetesimals, meaning the small early building blocks of planets. A comet nucleus belongs to this stage. It is not a late product of mature planetary weather or geology. It is an early leftover, assembled while the system is still young and while the disk still contains raw material not yet swept into larger worlds. For 3, I/Atlas. The chemistry suggests that this early assembly happens far from the central heat of its parent star. The abundance of volatile substances such as carbon dioxide and carbon monoxide, together with isotopic evidence for very cold conditions, points toward formation in a cold outer zone of that ancient disk. There, frozen molecules can accumulate onto grains and become part of growing icy bodies. The environment is dim, remote, and chemically rich in materials that cannot survive in warmer inner regions. The nucleus begins as one small member of a much larger population of icy remnants, forming at the outer edge of a young planetary architecture. This outer birthplace is likely crowded at first, though not in the sense of bodies touching one another constantly. It is crowded dynamically. Many planetesimals share overlapping paths. Gas still influences motion while the disk remains present. Larger embryos of planets are forming. Giant planets may already be growing from the same reservoir, especially if the system develops massive outer worlds. These larger bodies are crucial because they provide the most effective mechanism for ejecting small icy objects. A comet like 3I/Atlas does not leave its home system gently by drifting away on its own. It is usually expelled through gravitational scattering. Gravitational scattering happens when a smaller body passes close enough to a more massive object for its orbit to be strongly changed. In a young planetary system, giant planets are especially efficient at this. A small icy body can approach one of them and leave with the new direction and speed. Sometimes that means it is thrown inward toward the star. Sometimes it is sent into a distant bound orbit. Sometimes, if the geometry is right, it gains enough orbital energy to escape the star entirely. This is the most likely path by which 3I/Atlas becomes interstellar, a giant planet, or perhaps a chain of repeated encounters with giant planets, turns a native outer system remnant into a free body no longer bound to its first sun. The loss of such material is not unusual. In fact, it appears to be a normal consequence of planet formation. Young planetary systems are not tidy places. They build worlds by accretion, but they also discard enormous amounts of leftover matter. Some fragments collide and merge, some are broken apart, some are consumed by the star, some are flung outward and lost. Interstellar space is likely populated by countless such ejecta, bodies that once belonged to specific systems and later wander the galaxy unattached. In that broader context, 3I/Atlas is not an impossible exception. It is one example of a large and mostly unseen population created whenever planetary systems rearrange themselves and shed excess material. What makes this object special is not merely that it is ejected, but that it likely comes from an old system. The parent star may have formed billions of years before the Sun, in an era when the galaxy contains fewer heavy elements than in the Sun's natal environment. That older setting may influence both the chemistry of the disk and the dynamical history of the system. The comet then becomes a remnant not only of another star, but of another phase in galactic history. Its birth system is lost by name, yet partially preserved in the body's chemical and dynamical character. The parent system may also no longer exist in the form it once has. Planetary systems evolve, orbits shift, stars age. Some stars die quietly and lose outer layers. Some systems suffer instabilities that rearrange planets long after the gas disk is gone. Over the vast span suggested for 3I/Atlas, its birthplace may have changed beyond recognition, even if the star still survives somewhere in the thick disk of the Milky Way. This deepens the sense in which the home system is lost. It is not simply unlocated, it is likely transformed by time. Even so, the physical logic of that ancient home remains readable. There is a star. Around it lies a protoplanetary disk, meaning the disk from which planets form. In its cold outer zone, ices condense and stick to grains. A small icy body grows from those grains and retains a primitive mixture of volatiles. Larger planets grow as well. One or more of them eventually scatter the smaller body outward. Escape follows. The comet leaves its parent star and begins the interstellar life described in earlier regions. That chain of events is the most likely origin story available, not because one detail is observed directly, but because it matches the known physics of planetary formation and dynamical loss. This also marks the deep difference between 3I/Atlas and the oldest native materials found within the solar system. Meteorites preserve solids from the birth of the Sun's own disk, and those solids are ancient by any ordinary measure, but they belong to one local beginning. 3I/Atlas likely belongs to another beginning altogether, perhaps older, chemically distinct, and shaped in another system's cold outer reaches before being cast away. Its home is not the early solar system. Its home is another disk around another star, now separated from it by a history too long to retrace directly. So in this region, the comet resolves into a leftover of a vanished planetary nursery. It begins as a small icy body forming far from a different star, amid dust, gas, and giant planets still taking shape. It is preserved because it forms cold, and it is released because planetary systems throw away part of what they create. The exact star remains unknown, but the kind of birthplace is clear. 3I/Atlas is the surviving outer remnant of another system's early architecture, expelled from its first home and carried onward until the solar system briefly lies in its path. At the deepest level, 3I/Atlas is more than a comet passing through the solar system. It is a surviving piece of early planet formation from another star, preserved long enough to arrive as a material witness from an older part of the galaxy. The inward path now ends not in a smaller physical layer, but in the meaning of the material itself. The nucleus is ancient ice, dust, and rock. Yet those substances matter because they belong to one of the earlier stages in the making of planetary systems. They are not the polished products of long geological change. They're leftovers from assembly, stored in cold conditions and largely spared the kinds of transformation that erase a body's beginnings. Planet formation is efficient in one sense and wasteful in another. Around a young star, matter gathers into a disk and begins to organize itself into larger bodies, but only a fraction of that original material ends up inside finished planets. Much remains in smaller objects, especially in outer cold zones where growth is slower and distances are larger. These remnants can preserve the initial chemistry of the disk more faithfully than large worlds can. A planet evolves through internal heat, melting, differentiation, atmospheric change, impact reshaping, and in some cases volcanism or tectonics. A small icy nucleus does much less. It keeps rather than remakes. That is why an object like 3I/Atlas is valuable. It remains close to the raw state of a planetary system's beginning. This makes it a record of how early matter is sorted in space. In a young disk, temperature falls with distance from the star. That temperature gradient decides which materials can remain solid and which cannot. Close to the star, only the most refractory substances, meaning those that resist high heat, survive easily as solids. Farther out, water ice joins the solid inventory. Farther still, more volatile compounds can freeze as well. A body rich in water, carbon dioxide, carbon monoxide, and other primitive compounds therefore preserves evidence of formation in a very cold domain. In 3I/Atlas, that frozen inventory is not only a local fact about one comet, it is evidence that the same broad logic of disk chemistry works beyond the solar system too. Other stars make outer icy reservoirs, and those reservoirs build small bodies capable of surviving for immense spans of time. The comet also shows that early planetary material is not uniform across the galaxy. The Sun system forms in one chemical setting. Another star, especially an older star in an older galactic population, forms in another. The difference may be subtle in some elements and stronger in others, but it matters. The unusual isotopic patterns and volatile balance in 3I/Atlas indicate that early planetary solids can carry distinct signatures from the environments that produce them. This means that comet-like bodies from other systems are not merely copies of solar system comets under different names. They are samples of diversity in planetary birth. They show that the recipe for small icy bodies changes with galactic history, local chemistry, and the age of the parent stellar population. In this way, 3I/Atlas becomes a bridge between planetary science and galactic history. Planetary science usually studies how disks form planets, moons, and small bodies around individual stars. Galactic history studies how the Milky Way changes over billions of years through star formation, chemical enrichment, and orbital mixing. An old interstellar comet joins these scales. Its nucleus is tiny, but its meaning is large because it carries the chemistry of one young disk and the motion of one old galactic population at the same time. It shows that a very small body can preserve a connection between the earlier stage of planet building and the long aging of the galaxy around it. This connection helps explain why age matters so much in the interpretation of the object. If 3I/Atlas is older than the solar system, then it preserves material from a period when the Milky Way is younger and less chemically enriched than it is at the time the Sun forms. The galaxy at that earlier stage contains fewer heavy elements overall, and its stellar populations move in different dynamical patterns. A comet forming in that older environment may therefore record both colder chemistry and a more primitive galactic setting. The nucleus is then not only an early planetary remnant, it is a remnant from an earlier phase of the Milky Way's own development. This matters because most direct samples available to human study come from the solar system and therefore from one shared age. Meteorites preserve the birth of the Sun's disk. Lunar rocks preserve the history of one moon in that system. Mars, asteroids, and comets all belong to the same broad solar family. Even when they are ancient, they are local. An interstellar object breaks that locality. It broadens planetary science beyond one household of worlds. 3I/Atlas suggests that the archive of early planet formation is not locked inside the solar system alone. The galaxy itself is full of archived beginnings, and some of those beginnings occasionally pass within observational reach. Yet this object also teaches restraint. It does not reveal everything. It does not identify its parent star by name. It does not show a full untouched interior. It does not present an exact age written in matter. Observations indicate a very old interstellar comet from a chemically distinct environment, but important uncertainties remain. The full bulk composition is not known in perfect detail. The deepest untouched material cannot be sampled directly. The reconstruction of origin remains probabilistic. This limit is part of the meaning as well. Ancient objects do not surrender complete histories. They preserve fragments, and science works by fitting those fragments into the best physical account available. Even so, the fragments carried by 3I/Atlas are unusually rich. Its open orbit shows that planetary systems exchange matter with interstellar space. Its activity shows that old ices can survive that exchange. Its chemistry shows that cold outer disks around other stars build cometary bodies unlike the familiar ones around the Sun. Its motion shows that such a body can come from an older galactic population and arrive in the solar system only briefly before departing again. Taken together, these facts make the nucleus a rare natural sample of early planetary building blocks formed elsewhere and long ago. So the oldest object ever to enter the solar system is meaningful not because it is large or bright, but because it is old matter still carrying first conditions. It is a preserved remnant of an ancient disk, a piece of another system's beginning, and perhaps a messenger from an earlier Milky Way than the one that gives rise to the Sun. At the centre of the comet lies not only ice and dust, but a quiet record of how planets begin, how systems lose what they cannot keep, and how the galaxy stores those losses in the dark until one of them finally passes into view. The passage of 3I/Atlas through the solar system remains brief when set against the age it may carry. The Sun draws it inward, light loosens its surface, gas and dust spread around it, and then the same gravity that bends its path allows it to leave again. Nothing in its motion suggests that it will stay. It arrives as a visitor, becomes observable for a short time, and returns to the wider dark between stars. Yet during that short interval, an old material record enters reach. Its value lies in its quietness. It is a small body. It does not alter the planets. It does not reshape the architecture of the solar system. It simply passes through, carrying preserved ice dust, isotopic differences, and the motion of an older galactic history. In that way, it shows how much can remain stored inside a modest object. A nucleus only a few kilometers across can hold evidence of severe cold, distant formation, planetary scattering, interstellar survival, and a time before the sun begins to shine. Then the solar system releases it. The coma thins as conditions change. The tails are only temporary expressions of sunlight and solar wind. The nucleus remains the enduring part, small and dark at the center, continuing onward after observation fades. Telescopes collect data. Models improve. Uncertainty narrows in some places and remains in others. That is enough. The object does not need to give a complete history to reveal a meaningful one, so the mind can rest with the simplest image. Far beyond Earth, a very old body moves through the light of one star after ages in the dark between many stars. It crosses the sun's domain without belonging to it. It carries the memory of another beginning, then continues on through the Milky Way, returning to cold space with its long silence mostly intact.